Hey y'all, welcome back to our lecture number 9. This is going to be part 2, and we left off on slide 17, linear cost, revenue, and profit. Let's go ahead and get started. So these are just some definitions. The linear cost function models the cost, which we call C of x, to produce x items, where cost equals mx plus b, m being the variable cost and b being the fixed cost. A linear revenue function models revenue, which we call Rx, for selling x items. And the product P times X represents the price per item P times the number of items sold X. And then lastly, a linear profit function models the profit for producing and selling X items, where P of X is going to be equal to R of X minus C of X. And that kind of makes sense if you think about it. We have profit equals revenue minus cost. All right, let's jump into an example. At a summer art show, a vendor sells a lemonade for $2 per cup. The cost to rent the booth is $120. Furthermore, the art vendor knows that the lemons, sugar, and cups collectively cost 50 cents for each cup of lemonade produced. First, we need to write a linear cost function to produce X cups of lemonade. And remember, our linear cost function is C of X. So let's scroll back up and remember what our terms mean. C of X equals mx plus b. M is the variable cost here, and b is the fixed cost. So we know that they cost 50 cents for each cup. That means to produce X amount of cups, we are going to have to pay 50 cents, 0.5 times X, right? So if we do 1 cup, it's 50 cents. 2 cups, 2 times 50 cents is $1. So it's $1, and et cetera, et cetera, et cetera. So then we need to figure out what is our fixed cost. Well, our fixed cost is actually going to be the cost to rent the booth, which is $120, because that cost does not change no matter how many cups of lemonade we sell. We're still having to pay $120 to rent this booth. All right, next, write a linear revenue function for selling X cups of lemonade. So let's scroll back up here. So the linear revenue function is Rx equals Px, where the price per item is P. So that's going to be Rx equals 2x. Since we're charging $2 per third, write a linear profit function for producing and selling X cups of lemonade. Now remember, if we scroll back up here, linear profit is P of X equals R of X minus C of X. So P of X equals R of X minus C of X means we'll have P of X equals 2x, which is R of X, minus parentheses 0.5x plus 120. So we need to distribute this negative to get P of X equals 2x minus 0.5x plus minus 120. And then we can combine these like terms. 2 minus 0.5 is going to be 1.5x minus 120. All right, continuing the same example. How much profit will the vendor make if 50 cups of lemonade are produced and sold? So let me copy down my profit function. So we want to know how much we would make if 50 cups are sold. So that's saying that X is going to be equal to 50. So we'll have P of 50 is equal to 1.5 times 50 minus 120, which is going to be equal to 75 minus 120, which equals negative $45. So what this is saying is we are going to lose money if we only sell 50 cups. Next, how much profit will be made for producing and selling 128 cups? So that means X equals 128. We'll have P of 128 is equal to 1.5 times 128 minus 120. This is 192 minus 120, which is $72. Now I want to determine the break-even point. So what is a break-even point? Well, that means you break even where you make no money and you spend no money. Essentially, you profit $0, but you also don't lose any money. So that means P of X is going to equal 0. So we'll have 0 equals 1.5x minus 120, which means we'll have 120 equals 1.5x, and then we need to divide by 1.5 on each side, and we get x equals 80. So if we sell exactly 80 cups of lemonade, we will have lost no money. However, we will also have gained no money, and that's why it's called a break-even point. All right, let's keep going. All right, here are some parent graphs that y'all will need to remember. So first, we will look at the linear functions. So these are kind of what we've been graphing. If y'all will remember, this is a slope-intercept form, right? And then we have horizontal lines, constant functions. Next, we'll talk about the identity function. The identity function is called such a thing because we have when x equals 1, y is also going to equal 1. When x is 5, y is 5. When x is negative 3, y is negative 3, etc. You can see here in the table that all the x's and all the f of x's, which we also call the y's, are the same. Next is going to be a parabola, which is a quadratic function. So it's in the shape of a U. Third is going to be a cubic function. Then we'll have a square root function here. F of x equals square root of x. So we generally only like to pick x's that have square roots when we graph this. So that's why you see 0, 1, 4, 9, and 16. Because if you look over here at 4, the square root of 4 is 2. So we don't really want to pick like 6 because 6 doesn't have a really nice square root, so it's kind of difficult for us to graph that. But then if we pick 9, the square root of 9 is 3. So you can see that there. Next is going to be the cubed root function. And the cubed root is essentially the inverse of the cubic function here. So essentially if 2 cubed is equal to 8, that means that the cubed root of 8 is equal to 2. All right. Next is going to be the absolute value function. If you're not familiar with absolute value function, it essentially spits out the distance. So if you're looking at the absolute value of negative 2, you want to think about how many spaces away from 0 is negative 2. And that's going to be 2 spaces, even though it's to the left. So the absolute value of negative 2 is going to be 2. And then the absolute value of positive numbers, it just gives you back their positive numbers. So you get 1 and 1, 2 and 2, 3 and 3, 4 and 4, etc. Lastly, we have the reciprocal function, which is 1 over x. 1 over x, you just give me an x value and I give it the reciprocal. So if you give me 2, I give you a half. If you give me 3, I give you a third. You give me 4, I give you a fourth, and etc. Notice that we have no 0 values, and that is because we cannot do this, right? This is not okay. We cannot divide by 0. Okay, let's move on. So the reason we wanted to know about parent graphs is because we want to talk about graph translations. So if we consider a function defined by y equals f of x, and we let k and h represent positive real numbers, then the graph of y equals f of x plus k is the graph shifted k units upward. So when we add a number out here, outside, we're moving up. Similarly, when we subtract a number, we're moving down. Then when the number is inside of these parentheses here, so x minus h, we're shifting to the right, and x plus h, we're shifting to the left. So stuff outside of the f of x goes up and down, and stuff inside goes left and right. All right? All right, let's do some practice with this. So we want to graph the following translations. So the first one is x minus 1 quantity squared plus 2. So the parent graph we're going to use is y equals x squared. All right, so here is my parent graph. This is y equals x squared. So now what I want to do is graph this function using the translations that we discussed on the previous slide. So first, I know I'm going to go up 2. So if I shift any point, I like to pick the vertex, which is here. If I pick this point and I move it up 2 units, 1, 2, I would be here. However, it's also a minus 1. And remember, according to here, when it's minus, we're going to the right, all right? So that means I'm going 1 unit to the right. So this is 2 up, 1 to the right, which is going to be 1 this way, okay? So now I'm going to pick on this point. I'm going to go up 2 and over 1. So that's here. And you do that with each point. So here I have my new translated graph. So the parabola in the green would be your solution to this problem because we've shifted up 2 and right 1. The next problem, the parent graph, is going to be y equals the square root of x, which is going to look something like this. Y equals the square root of x. And remember, I'm just getting these parent functions from this spreadsheet up here that you have access to per this lecture note. So you can always come back and look at this nice little table if you forget what the parent functions look like, okay? So the square root of x was this function here, right? So now I need to identify what kind of shifts I'm doing. Well, this minus 2 tells me I'm going to go down 2. And this plus 3 inside of the x bit is telling me I'm going to go left 3. Because remember, per up here, if a plus is in here, then we're going to go left. All right. So I'm going to start with this point here. So down 2, left 3. All right? That means this point is going to start here. Next, I'll move the other points. I'll move them down 2 and left 3. This one is also going to go down 2 and then left 3. So it's here. Same with this guy. Down 2, left 3. let's move on. The other thing we can do with graphs is stretching and shrinking. So we can essentially pick up a graph and move it around. We can also stretch it out and shrink it. So consider a function defined by y equals f of x. Let a represent a positive real number. If a is bigger than 1, then the graph y equals a f of x is stretched vertically by a factor of a. However, if a is less than 1, then the graph is shrunk vertically by a factor of a. And then here's my example where you can see that this is the original function right here. I'm going to actually make it purple so y'all can see it a little better. But here's the original function, y equals x squared, right? If we multiply by 3, you can see here that it gets stretched vertically. So it's like we're pulling these two bits together. Like we're grabbing each of them and stretching them upward, all right? However, when we do a third x squared here, we are pushing them out. You can think about it as getting shrunk vertically. I like to think about it as pushing in and pushing out, but essentially this way it gets flatter, right? Here I just gave y'all a transformations table if y'all wanted to download the blank lecture slides and then just kind of save these for your own use. You can use this to look back on to remember all the transformations that you can do with a graph. Okay, let's use transformations on this graph to graph the function defined by n of x is equal to -1/2 times x minus 2 quantity squared plus 3. Okay, so first I'm going to identify the parent function, which is going to be y equals x squared. So I'm going to draw that first. Next, I'm going to do an intermediate step. I'm actually going to do something we're familiar with first. So I'm going to shift up 3 and right 2. Okay, so let's start with our vertex point per usual. We're going to go up 3 over 2. Now we need to follow that same suit with every single one of our points that we have on the graph. All right, so now here's my parabola with just the shifts. So now we were going to worry about this -1/2. So if we scroll up a bit, we can see that a negative in front of the function means we're going to reflect across the x-axis, okay? Also remember, from this example we just discussed, that if it is a fraction, essentially less than 1, we are going to have a stretch, like a flattening stretch. It's a vertical shrink, a horizontal stretch, but it'll flatten out a bit, essentially. So that means that we will have, if we scroll down, we're going to reflect horizontally, which is like here-ish, right? And we're going to slightly stretch, all right? Okay, so can y'all see how I kind of stretched it a little bit? Like if I would have just flipped it, if I would have just flipped this green one here, it would have been kind of like, to mirror it, it would have been like here-ish, right? So I just stretched it to make it a little bit flatter. So this blue line here would be your final answer. All right, let's move on. Next is symmetry. Consider an equation in the variables x and y. The graph of the equation is symmetric with respect to the y-axis if substituting in negative x for x in the equation results in an equivalent equation. For example, let's use our parabola. Y equals x squared. So you can also do f of x equals x squared. That would probably make more sense. So essentially, if we substitute in negative x, so f of negative x is equal to negative x squared. And then we remember that negative x squared is equal to negative x times negative x, and negative times a negative is a positive, so this is just x squared, right? We can see that f of x and f of negative x are both the same equation. So this would be symmetric with respect to the y-axis. We can also see that it's symmetric with respect to the y-axis by observation. Because if you look, here's the y-axis, and if you look, the y-axis almost behaves like a mirror for the two branches of my parabola, right? Okay, let's keep going. The graph of an equation is symmetric with respect to the x-axis if substituting negative y for y in the equation results in an equivalent equation. So I'm actually going to do an equation that is not technically a function. We're going to do x equals y squared. So if we substitute in negative y, we will get x equals negative y squared, which is y squared using the same rule that we used up here, right? Right up here. So also the graph of x equals y squared looks like this, where this is the x-axis. All right, and last, the graph of an equation is symmetric with respect to the origin if substituting negative x for x and negative y for y in the equation results in an equivalent equation. So I'm going to use the equation of a circle. So if we have x squared plus y squared equals 16, for example, this equation of a circle. If you plugged in negative x for x and negative y for y, well, remember that that negative x squared is equal to x squared, and negative y squared is equal to y squared. So this checks out. All right, moving on. So we want to determine the symmetry of the following. So first, we will do this equation of a circle. I may have spoiled the surprise with my previous example, but we're going to keep going. So first, we'll plug in negative x and negative y. Well, this is just x squared plus y squared. So we know that it is symmetric about the origin. Similarly, if you just plug in negative x squared, you'll get, again, x squared plus y squared equals 9. So it's also symmetric about the y-axis. Recalling from this definition up here, that if we substitute negative x for x, then it's symmetric with respect to the y-axis. And lastly, we'll plug in negative y. So we just get, again, x squared plus y squared equals 9. So it is also symmetric about the x-axis. Next, let's move on to number 2. So first, I want to plug in negative x, right? So absolute value of y equals negative x plus 1. This is not the same. So it is not symmetric about the y-axis. Let's plug in negative y. So absolute value of negative y equals x plus 1. And remember, we talked about absolute value a little bit earlier, but just kind of recall that the absolute value of y equals y and the absolute value of negative y equals y as well. So this is going to be absolute value of y equals x plus 1. So it would be symmetric about the x-axis. I'm sorry, I probably should have said that the absolute value of y is equal to the absolute value of negative y. That was my bad. Lastly, let's plug in both negative y and negative x. Here we end up again with y equal, absolute value of y equals negative x plus 1. And this is not the same as our original function, which had just an x and not a negative x. So the only symmetry is going to be about the x-axis for number 2. All right, let's move on. Even and odd functions. A function is even if f of x equals f of negative x for all x in the domain. The graph of an even function is symmetric with respect to the y-axis. A function is odd if f of x equals negative f of x for all x in the domain, and it is symmetric with respect to the origin. So remember that we had this similar definition for being symmetric with respect to the y-axis before. So I'm going to use the same example. So when we had y equals x squared, we knew that f of x was equal to f of negative x, since f of negative x was equal to negative x squared, which was equal to x squared, which was f of x, right? So what's tricky is going to be figuring out the odd functions. So let's take, for example, f of x equal to x cubed plus x, okay? So the first thing I'm going to do is plug in negative x. So f of negative x is going to be equal to negative x cubed minus x, right? Well, negative x cubed is just negative x cubed. If you're not familiar with the cubic function, I'll do a brief example kind of up here at the top. So if you have negative 2 cubed, that's equal to negative 2 times negative 2 times negative 2. And then here, negative times a negative is a positive, but we still have a negative left over. So this is negative 8. Okay? So and that's the same thing as negative 2 cubed, right? Okay. So we found f of negative x. That's here. Now I want to figure out what is negative f of x. You can think of negative f of x as negative 1 times f of x. So that's just going to be negative 1 times our function, which was x cubed plus x, right? So negative f of x is going to equal, once I distribute this negative x cubed minus x. So we can see here that we get the same thing. So this means that f of negative x is equal to negative f of x, and that this function is an odd function. Cool? All right, let's keep going. Determine if the function is even, odd, or neither. All right, let's just jump in with number 1. So we'll plug in f of negative x first. So that's going to be negative 2 times negative x to the 4th plus 5 times the absolute value of negative x. Okay? So remember that whenever we have an even power, our negatives will all cancel out. So negative x to the 4th is going to be the same thing as x to the 4th. And then remember that the absolute value of a negative is the same thing as the absolute value of its positive value. So now we have f of negative x is equal to our original function. So number 1 is going to be even. Let's move on to number 2. So we'll have g of negative x equals 4 times negative x cubed minus negative x. All right, that means g of negative x is going to be, we can pull this negative out front, negative 4x cubed. We can do that because this is an odd power. So odd powers keep the negative, even powers, they cancel out, right? And then here, once we distribute this negative, we'll get plus x. Okay, so this is not equal to g of x, right? This is not the same function. However, let's figure out what negative g of x is and see if that's going to be the same thing. So negative g of x is going to be the same thing as negative 1 multiplied by our original function. So now I just distribute the negative 1 in, and I get negative g of x is equal to negative 4x cubed plus x. And that is going to be the same thing as what we got when we plugged in negative x. So this means that g of negative x is equal to negative g of x, which means that the function is odd. Finally, let's do number 3. H of negative x equals 2 times negative x squared plus negative x. So h of negative x is 2x squared minus x. And since now this is a minus instead of a plus, this is not equal to the original function. So we'll go ahead and test out if it's going to be equal to negative h of x. So negative h of x is going to be negative 1 times 2x squared plus x. That means negative h of x is going to be negative 2x squared minus x. This is also not the same thing we got because now I have a negative in front of this 2 and I don't have one here. So that means h of negative x is not equal to negative h of x, and also h of negative x is not equal to h of x. Therefore, it is neither even nor odd. All right, let's move on. Next, we're going to talk about piecewise defined functions. So a piecewise defined function is essentially what it sounds like. It's a function defined in pieces. So if you think about splitting up a number line, when x goes from negative infinity all the way up to negative 1, we're going to graph this linear function here. When x is between negative 1 and 2, we're going to graph this constant function, negative 3. And then when x goes from 2 to infinity, we're going to graph this square root function, square root of x minus 2. So let me show y'all how we will do this. First, we're going to find these values that we were requested to find, and then we can put them on the graph. All right, let's start with f of negative 3. So when I'm finding f of negative 3 in a piecewise function, I first want to look at which interval it's in. The first one, the second one, or the third one. Since f of negative 3, since negative 3 is less than negative 1, it's going to be in the first one. So we're going to use negative x minus 1. So we get negative 3 minus 1. So that means f of negative 3 is equal to positive 3 minus 1, which is 2. So then I can write my point, negative 3 comma 2. So it means I'm going to go left 3, up 2. Next, I want to find f at negative 1. So when we look up here at our symbols, this one is telling us x is not negative 1. So when we're looking for f of -1, we're going to look here because this symbol means x can equal -1. So it's just going to be -3. So our point is going to be -1, -3. Next, we want f at 2. Again, we have to be tricky with our greater than symbols. So when we're looking here, this is strictly less than 2. So for my second one, x can't equal 2. However, on my third one, it is including 2. So I'm going to use my third equation to find f at 2. So this is going to be the square root of 2 minus 2, which is going to be equal to the square root of 0, which is 0. So that means I have the point 2, 0, which is here. Lastly, I need to find f of 6. So f of 6 is equal to the square root of 6 minus 2. I'm sorry, and we're using the third because the third one says only when x is bigger than 2 and 6 is bigger than 2. So that's why we're using this third function. So this is going to equal the square root of 4, which is 2. So f of 6 is equal to 2. Now I have 2 points on my third piecewise function. I'm going to graph the third one in purple. So I know that f of the square root of x makes this shape. So I'm just going to graph that shape. Next, I have a constant function, which is f of x equals -3. And it goes from -1 to 2, but it doesn't include 2. And what happens is that means we are going to leave a hole where the 2 would be. So if you did plug in 2, we'd get -3. However, we're not including it. So that means this graph is going to be the constant function at f of x equals -3, not including x equals 2. Lastly, we're going to graph -x minus 1. Now, x is strictly less than -1. So that means I need to leave a hole at where -1 would be. And where -1 would be, we can actually find out. There's going to be 1 minus 1, which is 0. So I actually need to leave a hole in my graph at the point -1, 0, which is right here. And then x minus 1 is a linear equation, so it's just going to be a line. And this is what a piecewise function looks like graphed. It's like little pieces of different graphs that you've just cut and pasted onto the same graph. All right? Let's move on. Increasing, decreasing, and constant functions. So a function is increasing if f of x1 is less than f of x2, provided that x1 is less than x2. Now what that means is if I have something like, let's say this was 2 and this was 3, right? So 2 is less than 3. That means their corresponding y values, f of 2 and f of 3. That means f of 2 needs to be less than f of 3. And that means a function is increasing. Similarly, if I have 2 and 3 here, 2 is less than 3. However, f of 2 is bigger than f of 3. That means my function is going to be decreasing. So as you increase your x value, if your function is getting smaller, it's decreasing. As you increase your x value, if your function is getting larger, that means it's increasing. And then over here, if it's staying the same, we call those constant functions. Alrighty. Our last example. For the graph of y equals g of x shown, determine where it is increasing, decreasing, and constant, then determine the location value of any relative maxima and minima. We are also going to talk about what these words mean. Maxima essentially just means, I like to think of it as a tall point, and minima as like a short point. So basically, when we're looking at this graph, we can see here that this is a point where the graph pivots. Any pivot point is always either going to be a relative max or min. It's going to be one or the other. So if we're looking at this pivot point in particular, we can see that all of the values are greater in the vertical direction. So this is actually going to be a relative minimum right here. Similarly, if we look at this one, we can see that on either side of this point, my graph is going up. So this one is also going to be a relative minimum. This pivot point here, my y values are going below it. So this is going to be a relative max. So that means my relative max is going to be at x equals 2, right? Because we can see here at x equals 2, we have this maximum point. And my relative min, my relative minimums, are going to be at x equals -1 and at x equals 4, right? All right, now let's figure out where we're increasing. So increasing means that as we get larger x values, we get larger y values, right? So if we look here, we can tell from this point to this point, as our x is getting larger, so is our y. So here we are increasing, right? We're also increasing from here onward. This arrow means we're assuming the graph does not come back down. So our 2 bits that we're increasing is going to be from -1 to 2 union 4 to infinity. Now, we always write increasing and decreasing in terms of x. So this is when x is -1 to when x is 2, and when x is 4 to infinity, right? Decreasing. It is decreasing from all the way up here, all the way down to here, right? It is also decreasing from here to here. So it's going to be decreasing from, well, what's x when we're going all the way up and up and up? It's going to be -infinity. So it's decreasing from -infinity all the way to -1. Union with 2 to 4. And again, these are x values. So from -infinity to when x is -1, and when x is 2 to when x is 4, our function is decreasing. Is how you would write that. All right, guys, that concludes part 2 of lecture 9. Thanks again so much for tuning in tonight. and I hope y'all have a wonderful rest of your day.